Right now, the farthest object humanity has ever built is screaming through the darkness at 38,000 miles per hour. Voyager 1 left Earth 48 years ago. It crossed into interstellar space 13 years ago, yet it will take another 30,000 years just to escape what we call our solar system. 30,000 years. Every empire that ever existed would rise and fall before that journey ends. If you enjoy learning about the limits we face, hit that like button and subscribe. The reality waiting in the void is far stranger than any dream. Prepare yourselves, we begin. Voyager 1 hurtles through absolute darkness at a speed that would cross the United States in 3 minutes. Every second, it travels 11 miles farther from home. The spacecraft launched in 1977. Back then, people still used rotary phones. The entire computing power aboard Voyager is less than your car key fob. Yet this tiny machine, weighing less than a small car, keeps transmitting data across a distance so vast it defies human comprehension. In 2012, scientists confirmed something extraordinary. Voyager 1 had crossed the heliopause, a boundary where our star's influence finally weakens. The solar wind that pushes outward from our home star stops there, blocked by the pressure of interstellar space itself. Instruments aboard the spacecraft detected the shift instantly. Charged particles from our star dropped by 1,000 times. Cosmic rays from distant explosions increased by 9%. The team literally jumped from their seats when they saw the readings. After 35 years of flight, humanity had sent something beyond the bubble. We had touched interstellar space. But here comes the twist that changes everything. Crossing that boundary means almost nothing for actually leaving our solar system. The heliopause sits at roughly 120 astronomical units from our star. 1 astronomical unit equals the distance from Earth to our star, about 93 million miles. Voyager traveled 120 times that far. Sounds impressive until you learn what lies ahead. The Oort cloud forms the true edge of our star's gravitational dominion. This spherical shell of icy bodies stretches outward in every direction. Conservative estimates place its inner edge at 1,000 astronomical units. The outer boundary reaches nearly 100,000 astronomical units from our star. Some scientists suggest it extends even farther, perhaps 200,000 astronomical units into the void. Do the math. Voyager sits at 169 astronomical units right now. The Oort cloud's inner edge waits at 1,000 astronomical units. The outer edge stretches to 100,000 astronomical units or beyond. At current speed, Voyager will take 300 years just to reach the inner Oort cloud. Passing through entirely? 30,000 years. Minimum. Think about that timescale. 30,000 years ago, humans were painting caves and hunting mammoth. Every civilization, every empire, every nation that ever existed happened within that span. The pyramids, Rome, the Renaissance, the Industrial Revolution, the space age itself, all of it fits within 30,000 years. Voyager would need that entire stretch of human history to escape. And Voyager represents our absolute best effort, our fastest, farthest, most successful attempt at reaching beyond. 48 years of travel, and we have barely begun. The machine will die long before it finishes. Its nuclear batteries lose 4 watts every year. By the early 2030s, silence will claim it. What comes next reveals an even darker truth. The heliopause feels like a finish line. Media reports celebrate it as leaving the solar system. Headlines announce humanity's first steps into interstellar space. Scientists know better. They use careful language, distinguishing between different boundaries. But the public hears what it wants to hear. We never actually left anything. The heliopause marks where charged particles from our star finally lose their battle against interstellar pressure. Imagine 2 winds colliding. Our star pushes outward constantly, ejecting plasma at 1,000,000 miles per hour. Interstellar medium, the thin gas between stars, pushes back. Where they balance, creates the heliopause. Think of it as the edge of our star's breadth, nothing more. Gravity extends far beyond breadth. Our star's gravitational reach defines the true boundary. Everything bound to our star, everything orbiting it, belongs to the solar system. The Oort cloud sits firmly within that grip. Those icy bodies circle our star in vast, slow orbits, lasting millions of years. They answer to our star's pull. They belong to us. Until something escapes that gravitational binding, it remains home. Voyager crossed into interstellar medium while remaining gravitationally trapped. The spacecraft entered the space between stars while still orbiting our star. It sounds contradictory until you grasp the scale involved. The gap between what our star's wind can reach and what its gravity can hold spans tens of thousands of astronomical units. That gap contains mostly emptiness, but also countless frozen objects. Long-period comets originate here. Every few centuries, one gets disturbed, begins falling inward, and humans witness a spectacular visitor. We see evidence of the Oort cloud regularly. We just never see the cloud itself. Too dark, too distant, too diffuse. Confirmed observations of Oort cloud objects remain theoretical. We know the cloud exists because comets must come from somewhere. We calculate its extent based on gravitational models and cometary orbits. Direct detection lies beyond our current capabilities. The objects are too small, too far, too dark to image. Our star's light, reaching that far, becomes vanishingly faint. 5 spacecraft currently travel on escape trajectories: Pioneer 10 and 11, both Voyagers, and New Horizons. All 5 will spend thousands of years traversing the Oort cloud. All 5 will eventually lose power and go silent long before completing the journey. All 5 technically remain within the solar system despite being humanity's farthest ambassadors. The heliopause creates a psychological boundary more than a physical one. It lets us feel like pioneers, like explorers reaching new frontiers. The reality is less romantic. We sent robots to the edge of our star's wind, and they confirmed what physics predicted. Impressive engineering, certainly. Leaving home? Not even close. The real edge waits so much farther ahead that human timescales become meaningless. We need to start measuring in geological epochs rather than generations. The distance from here to Alpha Centauri, our nearest neighboring star, equals roughly 268,000 astronomical units. The Oort cloud extends roughly halfway there. Interstellar space begins in our own backyard. The situation grows more troubling when you consider speed. Neptune orbits 30 times farther from our star than Earth does. 30 astronomical units. Humans consider Neptune the frontier, the edge of planetary territory, the last major body before emptiness begins. We visited it once, briefly, when Voyager 2 flew past in 1989. Getting there took 12 years. The Oort cloud begins 33 times farther than Neptune. Its outer reaches extend 3,000 times beyond Neptune's orbit. If Neptune feels impossibly distant, if 12 years to reach it seems like an eternity, then the Oort cloud represents a completely different category of remote. Picture this comparison. If Earth sat in downtown San Francisco, Neptune would be in Sacramento, about 90 miles away, doable in a car, right? The inner Oort cloud would start in Montana. The outer edge would reach beyond Alaska, past Hawaii, and into the middle of the Pacific Ocean. That single cloud, that shell of icy debris, occupies a volume larger than the entire planetary system by a factor of millions. Everything we consider space exploration happens in the tiniest fraction of the solar system's true extent. All human spaceflight, every satellite, every probe, every achievement, all of it occurs within a bubble so small compared to our star's domain that it barely registers. We are not spacefaring yet. We are barely shore waders. The objects themselves remain mostly mystery. Scientists believe they are ancient, pristine remnants from our star's formation. When the solar system condensed from a spinning disk of gas and dust 4.5 billion years ago, most material collected into our star and planets. The leftovers got scattered. Some stayed nearby, and formed the asteroid belt between Mars and Jupiter. Others were flung outward by gravitational interactions with the giant planets. Those became the Oort cloud. These bodies represent frozen time capsules. They contain the original chemistry of our stellar system, unchanged since its birth. Studying them could reveal how planets form, how organic molecules develop, how life's building blocks spread through space. The knowledge locked in the Oort cloud exceeds anything we might learn from 100 Mars missions. Yet reaching even one object requires technology we cannot currently imagine. The nearest confirmed Oort cloud object would take thousands of years to visit with present propulsion. Building something faster demands energy sources we have not invented. The challenge compounds exponentially with distance. New Horizons, our fastest planetary probe, travels at about 36,000 miles per hour relative to our star. Sounds fast until you calculate arrival times. New Horizons will take 20,000 years to travel 1 light year. The inner Oort cloud sits at roughly a quarter light year, 5,000 years minimum. The outer cloud extends beyond 1.5 light years, 30,000 years of travel time. These timescales exceed recorded history. They exceed agricultural civilization. They exceed behaviorally modern humans. We are talking about time spans that rival evolution itself. Nobody alive when a probe launches would see it arrive. Their children would not see it, nor their grandchildren, nor 100 generations beyond them. The mission planners themselves would become distant ancestors, forgotten legends to the descendants who finally receive data. What waits beyond stretches the mind even further. Light moves at exactly 186,000 miles every second. Nothing goes faster. Einstein proved this over a century ago, and every experiment since has confirmed it. Light speed represents an absolute limit, a cosmic speed limit enforced by the structure of space-time itself. This creates a brutal constraint. The nearest star system, Alpha Centauri, sits 4.25 light years away. Light itself takes 4.25 years to cross that gap. Any spacecraft we build must travel slower than light, meaning any journey takes longer than 4 years minimum. Realistically, much longer. Voyager moves at 0.006% light speed. At that rate, reaching Alpha Centauri takes 73,000 years. Even dramatically improving on Voyager gets us nowhere fast. Suppose we built something 10 times quicker, still takes 7,000 years. 100 times quicker, 700 years. 1,000 times quicker, 70 years. Only by reaching a significant fraction of light speed, say 10% or more, do timescales become remotely reasonable. 10% light speed gets you to Alpha Centauri in 42 years. 20% cuts it to 21 years. 50% brings it down to 8 years. Here is where physics becomes cruel. Reaching even 1% of light speed requires staggering amounts of energy. The faster you want to go, the more energy you need, and the relationship is not linear. It curves upward dramatically. Getting to 10% light speed requires 100 times more energy than getting to 1%. Reaching 50% demands 10,000 times more energy than 1%. And this assumes perfect efficiency, which violates thermodynamics. Real engines waste energy as heat. Real spacecraft need structural mass. Real missions require fuel for slowing down at the destination. Each requirement multiplies the problem. Chemical rockets, the kind that launched Voyager, cannot even approach 1% light speed. The energy density of chemical fuel is too low. You would need a fuel tank millions of times more massive than the payload. The rocket equation, a fundamental formula governing spaceflight, makes this mathematically impossible. You run out of universe before you run out of fuel requirements. Nuclear propulsion offers improvement. Fission and fusion reactions release millions of times more energy per kilogram than chemical bonds. Project Daedalus, a study from the 1970s, designed a theoretical fusion-powered starship. The design could reach 12% light speed. Journey time to nearby stars dropped to a few decades. Breakthrough, right? Wrong. The spacecraft required 50,000 tons of fuel, just the fuel. The fusion reactor and spacecraft structure added thousands more tons. Launching that mass from Earth would require thousands of rocket flights. The cost exceeded the gross domestic product of all nations combined, and Daedalus was unmanned, a tiny probe, no crew, no life support, no return journey. Antimatter rockets could theoretically reach 50% light speed or higher. When matter and antimatter collide, they annihilate completely, converting 100% of their mass into energy. Perfect efficiency. The ultimate fuel. Except antimatter does not exist naturally near Earth. We must create it artificially in particle accelerators. Current production rates: a few nanograms per year. A starship needs kilograms, maybe tons. At present rates, producing enough antimatter would take millions of years, and storing it presents its own nightmare. Antimatter annihilates on contact with normal matter, so containment requires perfect magnetic bottles. One failure, instant explosion. The energy requirements lead to an even stranger revelation. Accelerating 1 kilogram to 1% light speed requires 9 trillion joules of energy. That equals roughly 2 tons of TNT exploding. For every single kilogram, a modest spacecraft massing 1,000 kilograms needs 2,000 tons of TNT worth of energy just to reach 1% light speed. Now add fuel. Fuel has mass. That mass needs acceleration too, so you need extra energy to accelerate the fuel that accelerates the spacecraft, which needs more fuel to accelerate that fuel. The rocket equation creates a vicious cycle. By the time you account for fuel mass, realistic designs require fuel-to-payload ratios of 1 million to 1 or higher. 1 million kilograms of fuel for every kilogram of payload. 1,000 tons of fuel for a 1-gram spacecraft. To send something the size of a cell phone to another star at 1% light speed requires a fuel supply massing more than a Navy destroyer. Scaling up to a crewed mission becomes absurd. A spacecraft capable of supporting humans needs tens of thousands of kilograms minimum. The fuel requirements spiral into millions of tons. Launch costs make this economically impossible. Getting 1 kilogram into Earth orbit currently costs about $2,000 at absolute minimum, using the cheapest commercial rockets. Launching 1 million kilograms costs $2 billion. That is just to reach orbit. You still need to assemble the Starship, fuel it, and accelerate it to interstellar velocity. Total mission cost approaches hundreds of billions, possibly trillions of dollars, for a 1% light speed probe, for an unmanned mission, for a journey taking 400 years to reach Alpha Centauri. Time reveals another layer of difficulty. 400 years means 20 generations pass on Earth while the probe travels. The civilization that launches it will not resemble the civilization that receives data. Languages shift, nations rise and fall, technology transforms beyond recognition. Will anyone even remember the mission? Will the data format remain readable? Will anyone care? Historical precedent suggests not. Projects spanning multiple generations rarely maintain support. Cathedral construction in medieval Europe took centuries and often stopped halfway when priorities shifted. Deep ocean drilling programs get cancelled after decades. Multi-year scientific studies struggle for continued funding. Expecting 400-year commitment exceeds all examples. The human lifespan creates a fundamental barrier. People support projects they might live to see completed. Maybe projects their children might see. Grandchildren pushes the limit. Great-great-great-great-great-great-great-great-great-grandchildren? Nobody invests in that future. The payoff is too distant, too abstract, too disconnected from immediate concerns. And 1% light speed is glacially slow by interstellar standards. To make travel times remotely practical, to reach nearby stars within a human lifetime, speeds must approach 10% light speed or higher. Energy requirements increase by factors of 100. Fuel ratios explode. Costs multiply beyond imagination. Consider also the spacecraft's perspective. At 1% light speed, every second covers 1,800 miles. Interstellar space is not empty. It contains hydrogen atoms, about 1 per cubic centimeter. Sounds sparse until you are moving at 1% light speed. Each hydrogen atom you hit carries tremendous kinetic energy from the spacecraft's perspective. Dust grains become missiles. A grain of sand massing 1 milligram hits with the force of a hand grenade. Shielding becomes critical. Shielding adds mass. Mass requires more fuel. The cycle compounds. Then comes the hardest problem nobody talks about. Suppose we accepted the speed limits. Suppose we built a ship traveling at 1% light speed, taking 400 years to reach Alpha Centauri. Chemical and nuclear propulsion could theoretically achieve this, given enough fuel and money. The question shifts from, can we go fast, to, can we survive the journey? 400 years of travel demands. Multiple generations live and die aboard the spacecraft. The people who arrive are not the people who launch. They are descendants, born in space, raised in space, dying in space, never knowing Earth except through stories and videos. This concept, called a generation ship, represents humanity's most serious proposal for crewed interstellar travel. Building a generation ship solves one problem and creates a dozen others. Propulsion becomes easier because the ship accelerates slowly over decades. No extreme forces on the structure or crew, but everything else gets exponentially harder. The ship must function as a completely closed ecosystem, recycling air and water perfectly, growing food continuously, maintaining genetic diversity, preserving culture, educating new generations, and never, ever failing. Never failing is the critical constraint. If the oxygen recycler breaks on Earth, you call a technician. If it breaks on the International Space Station, you radio Houston for help or wait for a supply launch. If it breaks on a generation ship 3 light years from home, everyone dies. Communication delays mean Earth cannot help. Even at light speed, messages take years to arrive. By the time Earth receives a distress call, responds with instructions, and sends the reply back, decades have passed. The ship must carry every spare part it might need for 4 centuries. Every tool, every piece of machinery, complete manufacturing capability to fabricate replacements, probably raw materials too, since you cannot predict every failure mode. The mass quickly becomes enormous. Studies suggest a generation ship needs to mass at least 10,000 tons, possibly much more. Accelerating that to 1% light speed requires absurd fuel quantities. Population size creates another puzzle. Too few people and genetic diversity suffers. Inbreeding leads to genetic disorders within a few generations. Too many people and resource consumption overwhelms the life support systems. Studies suggest a minimum viable population of about 500 people. Some estimates go higher, requiring thousands to maintain genetic health and cultural stability over many generations. 500 to several thousand people living aboard a spacecraft for 400 years. They need housing, food production, water recycling, waste management, medical facilities, schools, recreation areas, manufacturing workshops, power generation. Everything a small town needs, all packed into a spacecraft, all required to work perfectly for centuries. Psychological challenges rival the engineering ones. These people are prisoners by any reasonable definition. They cannot leave. They cannot go outside. They cannot see natural landscapes. They experience the same corridors, the same faces, the same recycled air every day for their entire lives. Studies of Antarctic research stations and nuclear submarines show that even highly trained, mentally stable volunteers start experiencing psychological distress after months in confined spaces with limited social contact. Generation ship residents face not months but lifetimes of confinement. Children born aboard never chose this fate. They get no say in the mission. Their ancestors made the decision generations ago. Do they have a moral obligation to continue? What if they rebel? What if they decide to turn the ship around? What if they redirect to a different destination? Mission Control on Earth cannot enforce anything. By the time Earth learns, of course, changes. The ship is decades away from its last known position. Cultural drift becomes inevitable. Language evolves. Beliefs shift. The original mission goals might seem absurd to fourth or fifth generation crew. They did not sign up for this. Their great-great-grandparents did. But what authority do the dead hold over the living? Zero authority in any ethical framework. The people aboard the ship owe nothing to Earth. They might develop their own culture, their own priorities, their own objectives completely divorced from the original mission. The universe itself presents dangers even deadlier than isolation. Earth's magnetic field and atmosphere shield us from cosmic rays. These high-energy particles, mostly protons traveling near light speed, constantly bombard our planet. Few reach the surface. The ones that do rarely cause problems. Occasionally, a cosmic ray hits a computer chip and flips a bit, causing a random error. Passengers on high-altitude flights receive slightly elevated doses. Nothing serious. Space offers no protection. Cosmic rays pass through spacecraft hulls like bullets through paper. They pierce human cells, shattering DNA strands, triggering mutations, causing cancers, killing tissue. The longer someone spends in deep space, the more damage accumulates. On the International Space Station, astronauts receive 100 times more radiation than on Earth's surface. They limit stay durations to 6 or 12 months. Longer missions risk serious health consequences. A generation ship journey lasting 400 years means every single person aboard receives a lifetime dose of cosmic radiation. Not months, not years, decades. Their entire lives spent bathing in high-energy particles. The cancer rates would be catastrophic. Genetic damage would appear in children at alarming frequency. Average lifespan would plummet. Shielding helps, but not enough. Water provides decent shielding. Hydrogen atoms in water molecules absorb particle energy effectively. Surrounding living quarters with several meters of water tanks would reduce radiation exposure significantly, but several meters of water around all habitable spaces adds immense mass. Water is heavy. Moving that mass requires even more fuel. The ship grows larger, more massive, more expensive. Alternatively, you could use the spacecraft's fuel and supplies as radiation shielding, arranging them around the crew quarters. As the ship consumes fuel over decades, the shielding diminishes. Radiation exposure increases throughout the journey. Early generations receive better protection. Later generations suffer higher doses. By the time the ship nears its destination, fuel mostly depleted, radiation levels become extreme. Magnetic shielding offers another approach. Generate a powerful magnetic field around the spacecraft, mimicking Earth's protective magnetosphere. Charged particles like cosmic ray protons curve in magnetic fields, potentially deflecting them away from the ship. Sounds good in theory. Practice reveals problems. Creating a magnetic field strong enough to deflect cosmic rays requires superconducting magnets consuming tremendous power continuously. The energy demand never stops. Over 400 years, the total energy consumption becomes astronomical. Where does that energy come from? Nuclear reactors? Solar panels are useless in deep space, far from any star. Fusion reactors might work, but add mass and complexity. Even strong magnetic fields cannot stop all cosmic rays. The highest energy particles punch through anyway. These rare but deadly particles carry energies equivalent to macroscopic objects. A cosmic ray particle once detected in Utah hit with the energy of a baseball thrown at 60 miles per hour. Concentrated in a single subatomic particle, it tore through the detector like it was not there. No realistic shielding stops particles like that. You just hope they hit something non-critical. If one passes through a crew member's brain, instant death. rare but possible. Secondary radiation presents another threat. When cosmic rays strike shielding material, the collision produces a spray of secondary particles, neutrons, pions, gamma rays. These secondaries can be as dangerous as the primary cosmic ray. Heavy shielding might create more secondary radiation than it prevents. Optimal shielding requires careful material selection and specific thicknesses. Too little, primaries get through. Too much, secondaries become lethal. DNA repair mechanisms in cells can handle some radiation damage. Evolution designed these systems to cope with Earth's radiation environment. Deep space radiation exceeds that by orders of magnitude. Repair systems get overwhelmed. Errors accumulate faster than cells can fix them. Mutations stack up generation after generation. Genetic health of the population degrades. Studies suggest that after 20 or 30 generations in deep space, genetic damage might render the population non-viable. Sterility increases, birth defects rise, immune systems weaken. The mission dies from internal biological failure. But even perfect radiation shielding cannot solve another fundamental problem. Konstantin Tsiolkovsky derived the rocket equation in 1897. The math is simple and devastating. Every rocket must carry its own fuel. Fuel has mass. That mass needs acceleration. So you need extra fuel to accelerate the fuel, which needs more fuel to accelerate that extra fuel. The relationship is exponential. Small increases in desired velocity require massive increases in fuel. The equation looks like this. Change in velocity equals exhaust velocity times the natural logarithm of initial mass divided by final mass. To achieve high speeds, you need either tremendous exhaust velocity or a huge mass ratio. Chemical rockets have exhaust velocities around 2 miles per second. Nuclear thermal rockets might reach 5 to 10 miles per second. Ion drives achieve 30 to 50 miles per second, but with very low thrust. Even at 30 miles per second exhaust velocity, reaching 1% light speed, which is 1,800 miles per second, requires a mass ratio of 10 to the power of 26. That is 10 million billion to 1. For every kilogram of payload, you need 10 million billion kilograms of fuel. More mass than exists in the solar system. Physically impossible. The only way around this is staging. Build the spacecraft in stages. Fire the first stage, then jettison it. Fire the second stage with less mass to push. Jettison it. Continue until the final payload reaches desired velocity. Apollo rockets used 3 stages to reach orbit and the Moon. Interstellar missions would need dozens or hundreds of stages. The complexity becomes unmanageable. Each stage must be designed, built, tested, and perfectly synchronized with the others. One failure and the mission fails. Or you could avoid carrying fuel at all. External power sources solve the fuel mass problem. A laser beam from Earth could push a light sail, accelerating the spacecraft without onboard fuel. Breakthrough Starshot, a modern initiative, proposes exactly this. Use a massive laser array on Earth to push tiny light sail probes to 20% light speed. Journey time to Alpha Centauri drops to 20 years. Much more reasonable. Breakthrough Starshot probes would mass about 1 gram each. 1 gram total, including instruments, computer, communication system, camera, everything. Making something that small work is extremely difficult but theoretically possible with advanced miniaturization. The real problem is slowing down. The laser beam cannot reach the destination star. Once the probe passes beyond our stellar system, the beam spreads too wide to provide useful thrust. The probe has no fuel, no engine, nothing to slow itself. It screams past the target star at 20% light speed, taking a few hours of measurements, then continues into the void forever. A flyby, not a visit, no landing, no exploration, just a snapshot as it zooms past. For crewed missions, flybys are useless. Humans need to stop, explore, establish settlements. Stopping requires fuel, huge amounts of fuel. If you carry fuel for deceleration, the rocket equation kills you again. Half your fuel budget goes to slowing down, meaning you need massively more fuel for acceleration to achieve the same cruise speed. The mass ratios spiral completely out of control. Magnetic sails offer one theoretical solution. As the spacecraft approaches the destination star, it deploys a huge magnetic field. The star's solar wind pushes against this field, gradually slowing the spacecraft. No fuel needed. The problem is, solar wind is weak. Slowing down takes years or decades of gentle deceleration. You need to arrive at the star system with enough velocity left to capture into orbit, but not so much that braking takes forever. Threading that needle requires precise trajectory planning. Any miscalculation, and you either miss the target star entirely or fly past too fast to brake. Alternatively, the generation ship could carry a massive fuel reserve and use a fusion rocket for deceleration. This requires the fuel survive 400 years of storage. Cryogenic hydrogen boils off over time. Even in perfect tanks, some leakage is inevitable. 4 centuries of leakage depletes the tanks. You must carry extra fuel to compensate for losses, which makes the ship heavier, which requires more fuel for acceleration, which increases fuel for deceleration, which increases leakage rates. Another vicious cycle. Beamed power from the destination system could work if someone builds a laser array there first. Send a robot probe ahead, arriving centuries before the crewed ship. The probe builds solar panels, constructs a laser, and waits. When the generation ship arrives, the probe activates the laser, pushing against the ship's light sail to slow it down. Clever, but requires developing autonomous construction robots capable of building complex systems from local materials and hoping nothing breaks in the centuries between probe arrival and ship arrival. The probe has no spare parts, no repair capability. If it fails, the generation ship cannot stop. Some physicists propose something even more radical. When matter meets antimatter, both vanish in a flash of pure energy. The conversion is perfect. All mass becomes energy, according to Einstein's famous equation. 1 kilogram of antimatter plus 1 kilogram of matter releases 180 quadrillion joules. That equals 43 megatons of TNT. The largest nuclear bomb ever tested released 50 megatons. 1 kilogram of antimatter matches it. For rocketry, this represents the ultimate fuel. Nothing beats matter-antimatter annihilation for energy density. A starship powered by antimatter could accelerate to 50% light speed or more. Round-trip journeys become feasible. Slowing down at the destination uses antimatter fuel too. The spacecraft carries enough for both acceleration and deceleration. Journey times to nearby stars drop to decades instead of centuries. Many problems solve themselves when you have unlimited energy. The universe contains mostly matter. Antimatter exists rarely, created briefly in high-energy collisions like lightning strikes or cosmic ray impacts. But it annihilates almost instantly upon contacting normal matter. The Earth's crust, atmosphere, and biosphere are all matter. Antimatter cannot survive here. We must create it artificially. Particle accelerators, like CERN's Large Hadron Collider, produce antimatter in tiny quantities, smash protons together at extreme energies, and occasionally matter-antimatter pairs emerge from the energy of collision. The antimatter particles last microseconds before hitting normal matter and vanishing. Capture them before annihilation using electromagnetic traps. Store them in vacuum chambers surrounded by magnetic fields, preventing any contact with chamber walls. CERN produces about 10 million antiprotons per minute. Sounds like a lot until you do the math. 10 million antiprotons mass about 1 femtogram. That is 10 to the power of negative 15 grams. A millionth of a billionth of a gram. At this rate, producing 1 gram of antimatter takes 100 billion years. The universe itself is only 14 billion years old. Current production rates are 10,000 times too slow, even for geological timescales. Improving production requires building much larger accelerators. A facility dedicated to antimatter production, consuming enormous amounts of electrical power, might produce milligrams per year. Scaling up to grams per year demands accelerators the size of cities and power plants equivalent to large nations. The infrastructure investment reaches trillions of dollars, and that produces enough antimatter for one Starship per year. Multiple missions would require multiple facilities. Costs multiply. Storing antimatter safely presents its own nightmare. Any contact with normal matter causes instant annihilation. The containment vessel must keep antimatter suspended in perfect vacuum, using only magnetic fields. Failure means explosion. A milligram of antimatter releases energy equivalent to 43 tons of TNT. A gram equals the Hiroshima bomb. A kilogram creates a blast visible from space. Storing kilograms or tons aboard a spacecraft means one malfunction destroys everything instantly. No time to react, no emergency shutdown, no escape. The explosion would vaporize the ship and everyone aboard. Magnetic confinement requires continuous power. The magnets must never turn off. If power fails, containment fails. Antimatter touches the chamber walls. Detonation occurs. Starships, traveling for decades or centuries, need perfectly reliable power systems. Redundancy helps, but every system eventually fails given enough time. The longer the mission, the higher the probability of fatal malfunction. Cosmic ray impacts on the containment vessel could trigger failures too. A high-energy particle strikes the magnetic field generator, disrupts the field momentarily. Antimatter escapes confinement. Boom. Shielding the containment system adds mass. Mass requires more fuel. The ship grows heavier and more complex. Engineering challenges compound. Using antimatter for propulsion introduces additional problems. You cannot just annihilate matter and antimatter inside a rocket nozzle. The energy release produces gamma rays traveling in all directions. Most energy escapes without contributing to thrust. You need some way to direct the energy backward. Magnetic nozzles might work, channeling charged particles from the annihilation into a focused exhaust stream. But gamma rays are uncharged. They pass through magnetic fields, unaffected. Half the energy or more is wasted. Efficiency drops further when you account for antimatter production. Creating antimatter in accelerators consumes millions of times more energy than the antimatter stores. If you include production costs, antimatter becomes the least efficient fuel ever conceived. Using it makes sense only if you have unlimited energy and no other option. Neither condition applies. Earth has limited energy. Other propulsion options exist. Some scientists suggest harvesting antimatter from natural sources. Lightning produces tiny amounts. Cosmic ray collisions in the upper atmosphere create some. Theoretically, you could build collectors extracting antimatter from these processes. Reality check. The quantities are vanishingly small. You would need collectors the size of continents operating for centuries to gather micrograms. Not practical. Still, the possibility haunts researchers. Einstein's theory of relativity predicts that time flows differently for objects moving at high speeds. This is not science fiction. It is confirmed by countless experiments. Atomic clocks flown around the world on jet aircraft show measurably less time elapsed than identical clocks left on the ground. GPS satellites must account for relativistic time dilation, or their positioning calculations would error by miles. The effect is real and proven. At low speeds, time dilation is negligible. Jet aircraft experience only nanoseconds of difference. But approach light speed, and the effect becomes dramatic. At 90% light speed, every year experienced aboard the spacecraft equals over 2 years on Earth. At 99% light speed, 1 ship year equals 7 Earth years. At 99.9%, 1 ship year equals 22 Earth years. For interstellar travelers, this offers a strange gift. Journey times compress. A trip to a star 10 light-years away would take 10 years at light speed from Earth's perspective. But at 99.9% light speed, the travelers age less than 6 months each way. They experience a 1-year round trip while Earth ages 22 years. They could visit dozens of stars within their lifetimes while centuries pass on Earth. The price is profound. Return home and everyone you knew is old or dead. Your children are elderly. Your grandchildren have grandchildren. Culture has shifted beyond recognition. Language has drifted. You become a time traveler, leaping decades or centuries into the future with every journey. There is no going back. Time dilation only works forward, never in reverse. This transforms the psychology of interstellar travel. Crews become isolated not just by distance but by time. Communication with Earth grows increasingly meaningless. Years pass on Earth between transmissions. The people responding to your messages are not the people who received them. Conversations fragment across decades. Relationships become impossible to maintain. You are not just leaving Earth spatially but temporally. Families face impossible choices. If your parent joins a starship crew, you will likely never see them again. They age slowly. You age normally. By the time they return, you might be dead. Grandchildren might meet grandparents who appear younger than them. The social fabric tears apart. Civilizations change faster than starships travel. A mission launched in 1900 would return to find the internet, computers, smartphones, and social media. Language has evolved. Political systems have transformed completely. The crew would be strangers in their own homeworld, disconnected by time as much as by distance. They might not even recognize the culture that launched them. Velocity affects this dramatically. Moderate speeds produce manageable time dilation. At 50% light speed, time dilation is about 15%. A 10-year journey ages travelers 8.5 years. Noticeable but not devastating. Families stay somewhat synchronized. Communication remains feasible. Cultural drift stays manageable. High speeds create the severe effects. At 99% light speed, aging slows by a factor of 7. This speed demands tremendous energy. Getting even a small spacecraft to 99% light speed requires fuel quantities approaching the mass of small moons. The engineering becomes fantastical. Only antimatter or matter-antimatter annihilation provides sufficient energy density. All the problems mentioned earlier about antimatter production and storage apply with crushing force. Even if you solve the engineering, reaching such speeds takes years of continuous acceleration. One gravity of acceleration, comfortable for humans, increases velocity by 22 miles per hour every second. Reaching 99% light speed at 1 gravity requires 2.5 years of constant thrust. During acceleration, the ship consumes fuel constantly. The mass decreases, which means acceleration increases if thrust stays constant. Managing this requires sophisticated control systems. Too much acceleration kills the crew through excessive g-forces. Too little extends the acceleration phase, consuming more fuel through inefficiency. Then comes deceleration. Another 2.5 years of constant braking thrust. Total acceleration and deceleration time approaches 5 years. At these speeds, time dilation already becomes significant during the acceleration phase itself. Earth ages faster than the ship even before reaching cruise velocity. The temporal disconnect begins immediately upon departure. But even if time dilation worked perfectly, one barrier remains absolute. Light speed limits more than travel. It limits information. Nothing carries messages faster than light. Not radio waves, not laser beams, not quantum entanglement. Every form of communication obeys the same speed limit. Light speed sets an absolute maximum for how quickly information can travel between 2 points. At Alpha Centauri, 4.25 light years away, this means messages take 4.25 years to arrive. Ask Earth a question and wait 8.5 years for a reply. Simple conversations become impossible. Every exchange requires almost a decade. By the time you receive an answer, you have forgotten the question. Context evaporates across the years. Emergencies become fatal. Medical crisis aboard the ship. Earth's best doctors cannot help. Even if they diagnose instantly and transmit treatment instructions immediately, those instructions arrive years later. The patient dies long before help arrives. Equipment failure? Same problem. Earth's engineers cannot troubleshoot in real time. Solutions arrive years too late. Every crisis must be handled with onboard resources exclusively. Earth cannot assist despite wanting to. Mission control becomes meaningless at interstellar distances. During Apollo missions, controllers on Earth guided every maneuver, monitored every system, solved problems in real time. Communication delays were mere seconds. Astronauts could ask questions and receive answers fast enough to matter. At interstellar ranges, this connection breaks. The crew operates autonomously by necessity. Earth can send suggestions, but those suggestions describe a situation years out of date. Conditions aboard the ship have changed completely by the time advice arrives. The isolation is psychological torture. Humans need social connection. We evolved in tribes, surrounded by family and community. Even introverted people require occasional interaction with a broader society. Astronauts on the International Space Station maintain connections through constant video calls with Earth. Delays are negligible. They can talk to family in real time. That connection preserves sanity. Interstellar travelers lose this lifeline. Video calls become asynchronous. Send a message to your sister. Wait years for her reply. By the time she responds, your life has moved on. You are not the same person who sent the message. She is responding to someone who no longer exists. Relationships cannot survive this distortion. Even the strongest bonds fray and snap. Children born aboard the ship never experience Earth except through recordings. To them, Earth is myth, a distant origin story their grandparents tell. The communication delays make Earth unreal, an abstract concept rather than a tangible place. These children might not identify as human in the earthbound sense. They belong to the ship, to the void, to the journey itself. Earth is just a planet they have never visited and probably never will. Navigation becomes entirely autonomous. Course corrections require years of round-trip communication. Ask Earth to calculate a trajectory adjustment, and by the time the response arrives, the ship has moved billions of miles. The information is obsolete. Onboard computers must handle navigation independently. The crew must be trained to recalculate trajectories manually if computers fail. Backup systems need backups. Redundancy upon redundancy because help will not come. Scientific discoveries aboard the ship might never reach Earth. If the mission fails catastrophically, perhaps from collision with unseen debris, Earth learns about it 4 years later. No distress call, no warning, just silence where transmissions used to be. After years of silence, Earth concludes the mission failed, but the crew died years earlier. They were already ghosts by the time Earth stopped receiving signals. Data transmission faces its own obstacles. Beaming information across light years requires powerful transmitters and huge antennas. The inverse square law means signal strength drops with the square of distance. Double the distance, signal strength quarters. At interstellar ranges, signals weaken to almost nothing. Receivers on Earth must be enormous and incredibly sensitive to detect anything at all. Yet bandwidth is limited. Sending high-resolution images takes hours or days. Video is impractical. Text and compressed data only. Relativistic time dilation compounds communication problems. From Earth's perspective, the ship's clock runs slow. Messages from the ship arrive increasingly red-shifted and time-dilated. Signals stretch out, data rates drop, decoding becomes harder. From the ship's perspective, Earth appears to be running fast. Signals arrive blue-shifted and compressed. Information floods in too quickly. The temporal asymmetry breaks any sense of shared experience. You are not in conversation. You are exchanging messages with the past and future. Eventually, perhaps inevitably, the isolation breaks people. Submarines offer the closest analogy to interstellar spacecraft. Crews spend months sealed in metal tubes beneath the ocean, isolated from the outside world, breathing recycled air, seeing the same faces daily. Psychological screening is intense. Mental health monitoring is constant. Despite this, submariners experience elevated rates of depression, anxiety, and interpersonal conflict. 6 months underwater pushes human psychology to its limits. Now imagine not 6 months but a lifetime. Born aboard the ship, raised aboard the ship, dying aboard the ship without ever seeing open sky, feeling natural wind, or walking on solid ground. The psychological toll is unimaginable. No study has examined lifetime confinement because conducting such research would be unethical. We can only extrapolate from shorter confinements, and those extrapolations are grim. Antarctica research stations provide another data point. Winter overcrews stay for months in isolated bases during the dark season. Despite rigorous psychological screening, conflicts erupt regularly. Depression rates spike. Cognitive function declines. Social bonds fracture. People develop cabin fever, an actual psychological condition characterized by irritability, restlessness, and irrational behavior. These are trained professionals, volunteers who knew what they were signing up for, staying only months. Generation ship inhabitants face far worse conditions for their entire lives. Prisons teach us that long-term confinement damages the mind. Solitary confinement causes hallucinations, panic attacks, paranoia, and cognitive deterioration. Even in general population, long sentences produce psychological trauma. Inmates lose the ability to function in normal society. Decades of confinement reshape personality and cognition fundamentally. Now consider that generation ship residents are not criminals. They committed no crime, yet they are sentenced to lifetime confinement by the circumstances of their birth. Children especially suffer. Human development requires varied stimuli, natural environments, and social diversity. Children raised aboard ships experience none of this. Their world is corridors, recycled air, and the same few hundred faces forever. Studies of children in extremely isolated communities show developmental delays, limited worldview, and difficulty with abstract thinking. Generation ship children might never develop normal human psychological profiles. They become something else, adapted to their bizarre environment but unable to function anywhere else. Boredom becomes a constant enemy. Earth offers infinite variety, new places to visit, new people to meet, new experiences around every corner. The ship offers nothing new. You have seen every corridor, every room, every face, 1,000 times. Nothing surprises, nothing excites. Days blur into weeks, blur into years of monotonous sameness. Humans need novelty for psychological health. Without it, motivation collapses. Depression becomes universal. Purpose dissolves across generations. The first generation chose the mission. They have goals, dreams, reasons for going. Their children inherited the mission but did not choose it. The choice was made before they existed. They might resent this. By the third or fourth generation, the mission seems arbitrary. Why are we going there? Because great-great-grandparents decided to. That justification feels empty. Without strong purpose, morale crumbles. Social conflict becomes inevitable. Small communities cannot escape each other. On Earth, if you dislike someone, you avoid them. On the ship, avoidance is impossible. You see your enemies daily in the corridors, the cafeteria, the workshops. Feuds last lifetimes and spread to children and grandchildren. Vendettas span generations. Psychologists call this amplified conflict dynamics, where confined groups develop increasingly bitter divisions with no way to de-escalate. Mental illness rates would skyrocket. With no new genetic input, recessive genes for psychological disorders become more common through inbreeding. Depression, schizophrenia, anxiety disorders all increase in frequency. But the ship has limited medical resources. Advanced psychiatric care might not be available. Medication stockpiles might run out. Therapy requires trained professionals, and training new therapists across generations becomes difficult. Mental health deteriorates across the population with no way to stop it. Violence probably erupts periodically. Confined populations explode occasionally. Fights break out. Murders occur. With limited security and no external authority, maintaining order becomes difficult. The crew must police themselves, but police need training, resources, and legitimacy. If the population loses respect for authority, order collapses. The ship could descend into chaos, factions warring in the corridors, systems failing as violence disrupts maintenance schedules. Suicide rates might become alarming. People with no hope, no purpose, no joy, no escape might choose death. If suicide becomes culturally accepted, even encouraged, population decline accelerates. The mission fails because the crew chooses extinction over continuing. Yet the universe itself poses even colder threats. Kinetic energy equals 1/2 mass times velocity squared. This simple equation governs every moving object. Doubling the velocity quadruples the energy. Tripling velocity increases energy 9-fold. The relationship is exponential and brutal. A 1-gram object moving at 1% light speed carries 90 billion joules of kinetic energy. That equals 21 kilograms of TNT. For a single gram, a pencil eraser massing 1 gram needs the explosive equivalent of 50 pounds of TNT to reach 1% light speed. Scaling up to realistic spacecraft masses makes the numbers absurd. A modest probe, massing 1 kilogram, requires 90 trillion joules at 1% light speed. That is 21 tons of TNT worth of energy. A small car massing 1,000 kilograms needs 21,000 tons of TNT equivalent. A crewed spacecraft massing 10,000 kilograms requires 200,000 tons of TNT energy. These are minimum values assuming perfect efficiency, which violates thermodynamics. Real systems waste most energy as heat. Actual energy requirements could be 10 times higher. Where does this energy come from? Chemical rockets cannot provide it. Their energy density is too low. Nuclear reactions help, but still fall short. Fusion releases tremendous energy, about 10 million times more per kilogram than chemical reactions. A kilogram of fusion fuel releases about 300 trillion joules. Sounds like enough until you account for the rocket equation and efficiency losses. You need multiple kilograms of fuel per kilogram of spacecraft just to reach 1% light speed. For high mass ratios, hundreds or thousands of kilograms of fuel per kilogram of spacecraft. A 10,000 kilogram generation ship needs millions of kilograms of fuel. Launching that from Earth requires thousands of rocket flights. Each flight costs millions of dollars. Total launch costs reach hundreds of billions or trillions. And this only gets the fuel into orbit. Assembling the spacecraft, fueling it, and beginning the interstellar burn requires additional infrastructure. Space-based manufacturing, orbital fuel depots, massive construction facilities. The economic investment approaches the gross domestic product of major nations. Solar sails sidestep the fuel problem by using light pressure for propulsion. Photons carry momentum. Shine light on a reflective surface, and the surface experiences a gentle push. Make the surface area huge and mass tiny, and light pressure can accelerate the craft. Breakthrough Starshot proposes using ground-based lasers to push ultra-lightweight sails. The sail's mass only a few grams. Laser power provides acceleration without onboard fuel. The energy comes from Earth, not the spacecraft. But lasers consume power, a lot of power. Breakthrough Starshot envisions a laser array consuming about 100 gigawatts, comparable to 100 large power plants. Operating for minutes to accelerate a single probe to 20% light speed requires hundreds of billions of joules. Launching multiple probes demands repeated firings. The energy costs remain enormous even when fuel is not aboard the spacecraft. The laser beam spreads as it travels. Diffraction limits focus. By the time the beam reaches the probe, most light misses the sail entirely. Maybe 1% of laser energy actually pushes the probe. 99% is wasted, scattered into space. Efficiency is terrible. This is why the array needs 100 gigawatts to accelerate a 1-gram probe. Scaling up to larger probes or crewed missions requires power outputs exceeding anything human civilization has built. Particle beam propulsion offers slight advantages. Accelerate ions or electrons to high speeds and aim them at the spacecraft. Particles have more momentum per unit energy than photons. Better efficiency. But particle beams are harder to aim and spread faster than laser beams. Keeping the beam focused over light years might be impossible. Technology does not currently exist to do this reliably. Nuclear pulse propulsion throws nuclear bombs out the back of the spacecraft. Each bomb explodes, pushing against a massive steel plate attached to the ship. The explosions provide thrust. This sounds insane, but was seriously studied in Project Orion during the 1960s. Calculations showed it could work. A spacecraft powered by nuclear explosions could reach a few percent of light speed. Journey times dropped to centuries instead of millennia. The engineering is terrifying. The pusher plate must withstand thousands of nuclear blasts without breaking. The shock absorbers must be perfect or the crew gets pulverized. Radiation shielding becomes critical. Each explosion bathes the ship in gamma rays and neutrons. Even with shielding, crew exposure would be significant, and you need thousands of nuclear bombs. Building, storing, and safely deploying that many warheads requires infrastructure and expertise far beyond current capabilities. Environmental concerns also arise. Launching a spacecraft loaded with thousands of nukes from Earth risks catastrophic failure. One explosion during launch could devastate a continent. Assembly must occur in space, away from populated areas. But building nuclear weapons in orbit raises arms control issues. Treaties ban nuclear weapons in space. International cooperation would be necessary but politically difficult. Yet some proposals go even further into extreme territory. The Breakthrough Starshot Initiative, announced in 2016, aims to send tiny probes to Alpha Centauri within decades. The concept is elegantly simple. Build ultra-lightweight spacecraft, each massing about 1 gram. Attach them to ultra-thin reflective sails. Construct a massive laser array on Earth or in space. Fire the lasers at the sails. Light pressure accelerates the probes to 20% light speed in minutes. Journey time to Alpha Centauri drops to roughly 20 years. Total mission duration about 25 years, including acceleration and signal return time. 1 gram total mass. The entire spacecraft, including computer, sensors, camera, radio transmitter, and power supply, fits in a package smaller than a postage stamp. Modern microelectronics make this barely possible. Smartphones contain billions of transistors in chips massing grams. Miniaturization continues advancing. Eventually, a complete interstellar probe might fit on a single chip. Battery power is insufficient for a 20-year journey. The probe uses a tiny radioactive pellet generating electricity through decay heat. Enough power for basic functions and occasional transmissions. The sail is more challenging. It must be reflective, lightweight, and durable. A square meter of sail needs to mass less than 1/10 of a gram. Materials this thin barely exist. Graphene, a single atom-thick sheet of carbon, might work, but making square meters of perfect graphene remains extremely difficult. Defects weaken the structure. Micrometeoroids punch through. Laser heating causes thermal stress. The sail might tear or crumble during acceleration. Redundancy helps. Launch thousands of probes. If most fail, a few still reach the destination. The laser array is the real challenge. 100 gigawatts of laser power focused into a tight beam. This requires thousands of individual lasers synchronized perfectly. Each laser outputs megawatts. Cooling systems remove waste heat. Power plants feed the array. Control systems aim the beam with nanoradian precision. Any misalignment and the light misses the sail. Atmospheric turbulence distorts the beam. Adaptive optics correct in real time, but this is extremely difficult for such high power levels. The array probably needs to be space-based to avoid atmospheric problems. Building it in orbit requires launching millions of tons of equipment. Solar panels or nuclear reactors provide power. Assembly takes years or decades. Costs reach hundreds of billions of dollars. This is infrastructure for the entire initiative, not just one mission. Once built, the array can launch many probes over years. Targeting accuracy is critical. The probe accelerates for minutes, reaching 20% light speed. During acceleration, it travels thousands of miles. The laser must track it perfectly. Any deviation, and the light pressure stops pushing efficiently. The sail might tumble or drift off course. Guidance systems aboard the probe are minimal due to mass constraints. Steering is almost impossible. The initial aim must be perfect. The probe flies toward Alpha Centauri for 20 years. No power for course corrections. Gravity from our star and the target star bend the trajectory slightly. These effects must be calculated precisely before launch. Errors accumulate over light years. A small initial mistake results in missing the target star entirely. The probe might pass thousands of astronomical units away from Alpha Centauri, too far to observe anything useful. Assuming the probe arrives on target, it faces another problem: deceleration. The laser beam cannot reach the probe at Alpha Centauri. It has no fuel to slow down. It screams past the star system at 20% light speed. Transit time through the system is measured in hours. It gets one shot at observations. Cameras snap pictures. Sensors record data. Radio transmitter beams information back toward Earth. Then the probe vanishes into deep space, never to be recovered. 20 years of travel for a few hours of data collection. It is a flyby, not a visit. Still, even a flyby of the nearest star system would be revolutionary. Confirm planets exist. Measure magnetic fields. Detect biosignatures if life is present. The scientific value is immense. But getting data back requires the transmitter to work perfectly. After 20 years in space, exposed to cosmic rays and interstellar dust, will the electronics function? Redundancy is difficult when mass budgets are so tight. If the transmitter fails, the mission fails silently. Earth never receives data. The probe becomes another piece of space debris, invisible and forgotten. Received data takes 4.25 years to arrive. Total time from launch to first data reception is about 25 years. Within a human lifetime, mission planners might actually see results. This is psychologically important. People support projects they might live to see completed. Breakthrough Starshot also plans to photograph exoplanets around Alpha Centauri, high-resolution images of potentially habitable worlds. This requires incredible cameras. The probe is tiny. Optics are limited. Diffraction limits resolution. Still, even low-resolution images would be unprecedented, confirming water, clouds, continents, maybe even vegetation colors. Humanity's first glimpse of another world up close. Yet even this ambitious plan cannot solve one fundamental problem. Accelerating is relatively easy. You have fuel, you burn it. Thrust pushes you forward. As fuel depletes, your mass decreases. If thrust stays constant, acceleration increases. Efficiency improves. Speeds build. Given enough fuel and time, you reach a significant fraction of light speed. Slowing down is the mirror image and twice as hard. You must carry fuel for deceleration from the start. That fuel has mass. It needs acceleration too. The rocket equation strikes again. For every kilogram of fuel spent accelerating, you need an extra kilogram for braking. This doubles the fuel requirement. Doubling fuel mass means you need even more fuel to accelerate that extra fuel. Mass ratios explode exponentially. Consider a simple example. A spacecraft wants to reach 10% light speed and then stop at a target star. Assume an efficient fusion rocket with exhaust velocity of 30 miles per second. The rocket equation says the mass ratio for acceleration to 10% light speed is about 1 million to 1. You need 1 million kilograms of fuel for every kilogram of payload. Brutal, but theoretically possible. Now add deceleration. The spacecraft must carry deceleration fuel during acceleration. That fuel has mass. It needs accelerating too. Working through the math reveals the total mass ratio approaches 1 trillion to 1. 1 trillion kilograms of fuel for every kilogram of payload. A 1-gram probe requires 1,000 tons of fuel. A 1,000-kilogram crewed spacecraft requires 1 billion tons of fuel, more than the mass of a mountain. Launching that from Earth is physically impossible. Even assembling it in space from asteroid material would take centuries. Alternative methods exist but bring their own nightmares. Magnetic sails use the destination star's solar wind for braking. No fuel required, but solar wind is weak. Slowing from 10% light speed takes years of constant deceleration. The sail must be enormous, hundreds of kilometers across. Deploying such a structure is incredibly difficult, and it only works near stars. Interstellar space has no solar wind. You cannot brake mid-journey. You must coast until reaching the destination star, hoping you aimed perfectly and can brake in time. Gravitational slingshots offer another approach. Approach a planet or star at high speed. Gravity curves your trajectory, altering your velocity vector. Done correctly, you shed velocity relative to the star system. Multiple flybys can slow you further. This technique requires precise navigation and favorable planetary positions. If planets are not where you need them when you arrive, the maneuver fails, and you still need some propulsion for final adjustments. Gravity alone rarely puts you in perfect orbit. Aerobraking dips the spacecraft into a planet's atmosphere. Atmospheric drag slows you, no fuel needed. The downside is obvious. Hitting an atmosphere at 10% light speed generates unimaginable heat. The spacecraft becomes a meteor, glowing white-hot, shedding plasma. Heat shields protect the crew, but only up to a point. Most materials vaporize at the temperatures involved. You would need exotic heat shields made from materials that do not exist yet, and finding a planet with the right atmospheric density is tricky. Too thin, insufficient braking. Too thick, you burn up. Beamed power from the destination offers an elegant solution, but requires infrastructure. A previous mission sent robots decades earlier. The robots constructed solar panels, built a laser, and waited. When the crewed ship arrives, the laser activates, pushing against the ship's sail, breaking it. This works beautifully in theory. Practice reveals issues. The robots must function perfectly for decades. They must survive cosmic rays, dust impacts, and equipment wear. If any critical component fails, the laser does not work. The crewed ship cannot slow down. It flies past the star system and into the void forever. The crew dies slowly as supplies run out. Antimatter rockets solve the problem by having absurd fuel energy density. Carry enough antimatter for both acceleration and deceleration. Seems simple until you remember antimatter's problems. Production rates are infinitesimal. Storage is nightmarishly dangerous. Costs exceed planetary budgets. Antimatter solves the physics problem by creating unsolvable engineering and economic problems. Some physicists propose multi-generation missions that never stop. The ship passes through the destination star system at high speed, observing as it goes, then continues to the next star, and the next, generation after generation living aboard, visiting star systems every few decades. The descendants never stop, never land, never leave the ship. They become permanent nomads of the void. This avoids the deceleration problem entirely by embracing perpetual motion. The philosophy is bleak. You are not traveling to somewhere. You are traveling through everywhere, never arriving, never settling, never stopping. The journey itself becomes the destination. For some, this might be acceptable. For most, it sounds like hell. Humans want homes, not eternal transit. But suppose you somehow solved every problem so far. One more barrier waits. Space is not empty. Even in the vast gulfs between stars, a few hydrogen atoms drift in every cubic centimeter. Dust grains, tiny solid particles, float scattered throughout the void. Concentrations vary. Near stars, the density increases. In deep interstellar space, matter becomes extremely sparse. But sparse does not mean absent. At relativistic speeds, even a single atom becomes a projectile. Physics is merciless. Kinetic energy equals 1/2 mass times velocity squared. At 10% light speed, a hydrogen atom hits with the energy of a bullet. Not metaphorically, literally. The energy scales match. One atom, traveling at 10% light speed relative to the spacecraft, impacts with enough energy to penetrate metal. The spacecraft is stationary from its own perspective. The atom is the projectile. Impact speeds are identical whether the ship hits the atom or the atom hits the ship. Physics does not care. Hydrogen atoms are everywhere. The ship plows through them constantly. Each impact releases energy. The spacecraft's forward surface heats up. At low speeds, this heat is negligible. At relativistic speeds, it becomes a blowtorch. The erosion rate increases exponentially with velocity. 10% light speed produces moderate erosion. 20% causes severe erosion. 50% and the front of the ship glows red hot, boiling away. Shielding helps but adds mass. A thick layer of sacrificial material, something that erodes slowly, protects the spacecraft. But every kilogram of shielding needs acceleration. More mass means more fuel. The rocket equation applies. Shielding makes the ship heavier, which requires more fuel, which makes it heavier still. The design spirals toward impracticality. Dust grains are worse. A grain massing 1 microgram, smaller than a speck of dust visible to the eye, hits with the force of a hand grenade at 10% light speed. 1 microgram is 1/1,000,000th of a gram. Negligible mass, tremendous energy. The grain punches through shielding, penetrates the hull, and detonates inside the spacecraft. Crew compartments become shrapnel-filled kill zones. Dust grain impacts are random. You cannot predict when or where they hit. Detection is nearly impossible. Radar does not work at these scales. Optical systems might see large grains seconds before impact. Not enough time to maneuver. A spacecraft traveling 10% light speed covers 1,800 miles every second. Even if sensors detect a grain 10 seconds out, the ship travels 18,000 miles during those 10 seconds. Evading requires instant acceleration perpendicular to the flight path. The G-forces would crush the crew. Electromagnetic deflection might work for charged particles. A powerful magnetic field around the spacecraft curves the trajectory of incoming ions. They miss the ship, but magnetic fields require constant energy. Superconducting magnets consume significant power. Over decades of travel, the total energy requirement becomes substantial, and magnetic fields do not affect neutral atoms or uncharged dust. Half the threats pass through undeflected. Whipple shields use multiple thin layers spaced apart. An incoming particle hits the first layer and vaporizes. The vapor cloud spreads. It hits the second layer with lower energy per unit area. Multiple layers dissipate the impact across a larger area. This works for low-velocity impacts like orbital debris around Earth. At relativistic speeds, the vapor cloud is still hypervelocity. It punches through subsequent layers like they are tissue paper. Whipple shields become ineffective. Some scientists suggest using ice or water as forward shielding. Water is abundant in space. Comets and asteroids contain it. Harvest ice, pile it on the front of the spacecraft, and let it absorb impacts. Water vaporizes on impact, carrying away energy. Fresh ice replaces eroded ice continuously. This requires mining asteroids during the journey, processing ice, and repairing the shield. All doable in principle but enormously complex in practice. Laser ablation offers active defense. mount powerful lasers on the spacecraft, detect incoming grains, fire lasers to vaporize them before impact. This requires incredible precision. The lasers must hit microgram-sized targets kilometers away, while both objects travel at relativistic speeds. Computer targeting systems must calculate interception angles, accounting for relativistic effects. Miss rate would be high. Even 1% of grains getting through could be fatal over decades of flight. The distribution of interstellar matter is poorly understood. We know average densities, but local variations exist. Denser regions, perhaps near old supernova remnants or molecular clouds, could have concentrations 10 or 100 times higher than average. If a starship enters such a region unknowingly, impact rates spike. The ship might encounter thousands of grain strikes per second instead of a few per hour. Shielding erodes catastrophically. The mission fails in minutes. Mapping interstellar dust distributions requires detailed surveys from Earth. Telescopes can observe dust clouds light years away. Mission planners use this data to plot safe routes. But observations have limited resolution. Small clouds might go undetected, and dust distributions change over time. Stellar winds, supernovas, and galactic dynamics shift matter around. A route surveyed before launch might be hazardous decades later when the ship arrives. There is no real-time update. The crew must trust decades-old maps. Even if shielding works perfectly, even if every dust grain is avoided or absorbed, even if the ship survives the entire journey intact, human biology still creates insurmountable barriers that technology cannot fix. Gravity shapes every system in the human body. Your heart pumps against it. Your bones support weight because of it. Your inner ear detects balance using it. Evolution designed us for one gravity, the pull we feel standing on Earth's surface. Remove gravity, and biology breaks down. Astronauts on the International Space Station lose bone mass rapidly. Up to 13% of back muscle disappears in just 8 days. Bones shed calcium continuously. The body thinks it does not need strong bones anymore. Why maintain heavy skeletons when there is no weight to bear? Astronauts drink milk fortified with extra calcium. They exercise 2 hours daily on resistance machines. Bone loss slows but never stops completely. 6-month missions result in measurable skeletal weakening. Return to Earth and recovery begins, but it takes months. Some damage never heals. The longer someone stays in space, the more permanent the deterioration becomes. Astronauts who spend a year in orbit might never fully recover bone density. Their fracture risk remains elevated for life. Now imagine an entire life in weightlessness. Children born aboard a generation ship experience zero gravity from conception. Their skeletons never learn to support weight. Why would they? There is no weight. Bones develop thin and fragile. Muscles remain weak. These children could never survive Earth's gravity. Bring them home and their skeletons collapse under their own body weight. Ribs crack. Spines compress. Legs break. They suffocate because chest muscles cannot lift the ribcage against gravity. Generation ship inhabitants become irreversibly adapted to weightlessness. They cannot leave the ship. Even landing on the destination planet becomes impossible unless it has much lower gravity than Earth. Mars has 38% Earth gravity. Maybe survivable for spaceborne humans. Europa has only 13%, better odds. An Earth-like world with full gravity? Fatal. Cardiovascular systems fail in similar ways. Hearts do not need to pump hard against gravity in space. Blood pressure drops. The heart weakens, becomes smaller, more efficient for zero gravity but useless for planetary surfaces. Return someone to gravity and blood pools in their legs. The heart cannot pump hard enough. They pass out when standing. Prolonged exposure causes permanent cardiac damage. Fluid distribution shifts upward in weightlessness. On Earth, gravity pulls fluids downward. Blood accumulates in legs. Stand too long and feet swell. In space, fluids float upward toward the head. Faces become puffy. Sinuses stay congested. Pressure builds inside the skull. This affects vision. The eyeballs change shape, optic nerves swell, astronauts develop farsightedness. Some experience permanent vision degradation after long missions. Children developing in zero gravity might have severely abnormal visual systems. The pressure changes during growth could cause developmental defects. Strabismus, amblyopia, or even blindness might become common. Medical interventions could help but require resources and expertise that might not be available aboard a generation ship. The immune system weakens in space. Studies show T-cell function declines. White blood cells become less effective. Astronauts get sick more easily. Wounds heal slower. Infections are more dangerous. The mechanisms are not fully understood. Perhaps the lack of gravity affects cell signaling. Perhaps cosmic radiation damages immune cells. Either way, spaceborne humans would have compromised immune systems from birth. Disease outbreaks could devastate the population. Pregnancy in zero gravity has never been studied in humans. Animals sent to space show developmental abnormalities in offspring. Rats born in space have balance problems. Their inner ears develop incorrectly. Some fish embryos develop without proper skeletal structure. The fluid dynamics of pregnancy depend on gravity. Amniotic fluid, placental blood flow, fetal positioning, all assume gravity exists. Remove it, and complications probably arise. Miscarriage rates might spike. Birth defects could become common. The population might struggle to reproduce successfully. Artificial gravity offers a solution. Spin the spacecraft. Centrifugal force mimics gravity. Engineering determines the details. A rotating cylinder or ring generates force proportional to radius and spin rate. Humans tolerate rotation up to about 2 revolutions per minute without motion sickness. Larger radius means slower rotation for the same artificial gravity. A ring 100 meters in radius spinning at 2 RPM generates roughly 1/4 Earth gravity, tolerable but weaker than ideal. Building a rotating generation ship requires enormous structural engineering. The ship must balance perfectly or wobble during rotation. Imbalance creates stress, vibration, and eventual structural failure. Every system must function while spinning. Docking becomes complex. Visiting craft must match rotation before connecting. The complexity multiplies every subsystem, yet even perfect artificial gravity cannot solve another fundamental challenge. Life on Earth depends on an open system. Energy pours in from our star. Waste heat radiates into space. Matter cycles, but is not perfectly closed. Dead organisms decay. Nutrients leach into oceans and soil. Rain replenishes water. Atmosphere exchanges gases. The biosphere is vast, resilient, and self-correcting. Temporary imbalances fix themselves over time. A generation ship has none of these advantages. It is a closed system. Almost no matter enters. Almost none leaves. Everything must be recycled endlessly. Air, water, food, waste, all cycle through biological and chemical processes. One broken link and the entire system collapses. Everyone dies. Oxygen production requires plants or algae. Photosynthesis converts carbon dioxide and water into oxygen and carbohydrates. Simple chemistry. The challenge is scale. Each human needs about 20 cubic meters of oxygen daily. 500 people need 10,000 cubic meters per day. Plants produce oxygen slowly. You need vast farms, greenhouses spanning hectares. Growing that much plant mass requires light, water, nutrients, and space, all limited aboard a spacecraft. Artificial lighting consumes power. Sunlight is free on Earth. In deep space, the nearest star is too distant. Artificial lights must run constantly. LEDs are efficient, but still need energy. Over decades, the cumulative power requirement is massive. Nuclear reactors supply power, but fuel is finite. Fusion might provide decades of energy if the technology matures. If not, the ship goes dark, plants die, oxygen production stops, the crew suffocates. Water recycling must approach 100% efficiency. Every drop of sweat, urine, and moisture in breath must be captured and purified. The International Space Station recycles about 93% of water. The remaining 7% is lost to inefficiency, acceptable for short missions, fatal for generation ships. 7% loss means supplies deplete in 15 years. You need 98 or 99% efficiency. Achieving this is extremely difficult. Filters and membranes wear out. They need replacement. Spare parts take up space and mass. Running out of filters means water becomes contaminated. Bacteria, salts, and toxins accumulate. Drinking the water causes illness and death. Manufacturing replacement filters aboard the ship requires raw materials and equipment, chemical processes, polymer synthesis, precision fabrication, all complex, all prone to failure. Food production faces similar constraints. Humans need calories, proteins, fats, vitamins, minerals. Variety is important for health and morale. A diet of only algae paste is nutritionally complete but psychologically unbearable. People need flavor, texture, choice. Growing diverse crops requires different environmental conditions. Tomatoes need different temperatures and light levels than wheat. Managing multiple growth environments increases complexity. Soil is heavy. Hydroponics, growing plants in nutrient water without soil, saves mass. But hydroponic systems need precise chemical balance. Too much nitrogen burns roots. Too little phosphorus stunts growth. pH must stay within narrow ranges. Automated systems monitor and adjust continuously. Sensors fail. Computers glitch. Backup systems help, but add redundancy and complexity. Pests and diseases threaten crops. Aphids, mites, fungi, bacteria, all can devastate harvests. On Earth, predators and environmental factors control pests naturally. On the ship, no natural predators exist unless you bring them. Introducing predators creates new ecological complications. Balancing pest-predator populations in a closed system is incredibly difficult. Overshoot leads to collapse. Crops die. Food supplies vanish. Starvation follows. Pollinators like bees require specialized care. Bees need hives, flowers for nectar, and specific temperature ranges. Managing bee colonies in space is challenging. Bees might become disoriented in low gravity. They might fail to pollinate effectively. Hand pollination is labor-intensive and time-consuming. Thousands of flowers need attention daily. The crew spends all day pollinating instead of maintaining critical systems. Waste management is equally critical. Human waste contains nitrogen, phosphorus, and organic matter, useful nutrients if properly recycled. Composting breaks down waste biologically. Bacteria digest organics, releasing nutrients for plants. The process produces heat and gases. Controlling it requires monitoring oxygen levels, temperature, and moisture. Too hot, and the bacteria die. Too cold and decomposition stops. Too wet and anaerobic bacteria produce toxic hydrogen sulfide. Too dry, and the process halts. Mechanical failures in any subsystem cascade through the entire ecology. Recycler breaks, waste accumulates, toxins build up, air scrubber fails, carbon dioxide levels rise, crew suffocates, water purifier malfunctions, contamination spreads, disease erupts. Each system depends on others. Redundancy helps, but every redundant system adds mass, complexity, and more failure points. Perfect reliability over centuries is probably impossible. Even minor inefficiencies compound over generations. Lose 0.1% of oxygen per year to leakage or chemical binding. Seems trivial. After 200 years, total loss is 20%. You started with enough for 500 people. Now you have enough for 400. The extra hundreds suffocate slowly. The ecosystem contracts. Carrying capacity drops. Population must decline or everyone dies. Yet even perfect ecological balance cannot prevent another category of catastrophe. Machines fail, bearings wear, circuits fry, Pipes corrode. Metal fatigues from repeated stress. Entropy is relentless. Every physical system degrades over time. Maintenance slows the process. Eventually, replacement becomes necessary. On Earth, you order parts or buy new equipment. On a generation ship light years from home, neither option exists. The ship must carry spare parts for everything: pumps, valves, filters, sensors, computers, cables, seals, everything. Estimating quantities is guesswork. How many pumps fail in 100 years? Maybe 5, maybe 50. Nobody knows for certain. Manufacturing is not perfectly consistent. Some parts last decades, others fail within months. You cannot predict individual failures. You stock extras and hope. Storage is limited. A pump spare for a system that might fail takes space better used for food or water reserves. Over-provisioning wastes mass. Under-provisioning guarantees eventual shortages. Mission planners make educated guesses. Sometimes they guess wrong. Manufacture your own parts aboard the ship. Sounds reasonable. Requires complete machine shops, raw materials, and trained technicians. Machining metal parts needs lathes, mills, drills. Electronics require fabrication equipment, clean rooms, and chemical supplies. Producing circuit boards from scratch involves complex processes: etching copper, depositing silicon layers, doping semiconductors. Difficult on Earth with established supply chains. Vastly harder aboard a spacecraft with limited resources. Training crosses generations. The first generation includes engineers trained on Earth. They know how to repair, machine, and improvise. They teach the next generation. Knowledge passes down verbally, through manuals and hands-on apprenticeship. But skills degrade through transmission. Details get lost, nuances forgotten. By the 4th or 5th generation, critical knowledge might vanish. Nobody remembers why certain procedures exist. Nobody understands the original design principles. Written documentation helps preserve knowledge. Manuals, diagrams, videos, all stored digitally. Digital storage degrades over time. Magnetic media lose data within decades. Solid-state drives experience bit rot. Optical discs deteriorate. Redundant copies help, but all copies age together. Refresh the data periodically by copying to new storage. This requires working computers and power. If computers fail before data gets refreshed, information is lost permanently. Catastrophic failures kill everyone quickly. The main reactor shuts down unexpectedly. Power vanishes. Life support stops. Carbon dioxide scrubbers go offline. Within hours, CO2 reaches toxic levels. Within days, everyone is unconscious. Within a week, everyone is dead. Backup power provides time to fix the reactor. Hours or days depending on battery capacity. If the repair takes longer, if the problem is too complex, if the necessary parts are unavailable, the crew dies. Redundancy mitigates single-point failures. 2 reactors instead of 1. If the primary fails, the backup activates. Sounds good until both fail simultaneously. Common cause failures happen. A software bug affects both reactors. A coolant line shared between systems ruptures. Design flaws manifest in all redundant components at once. Redundancy reduces risk but does not eliminate it. Some failures develop slowly. A crack forms in a water tank, tiny at first, slowly growing. Water seeps out unnoticed. By the time someone notices the leak, thousands of liters have been lost. Water reserves drop below critical thresholds. Rationing begins immediately. Bathing stops. Drinking water is measured carefully. Crop irrigation is reduced. Plants produce less food. Hunger follows. Morale collapses. Social order frays. The crew might survive, but the mission is compromised. Repairing certain systems is physically impossible aboard a cramped spacecraft. Suppose a primary structural member cracks. The ship's spine, the central tube connecting modules, develops a stress fracture. Repairing it requires removing surrounding modules, cutting out the damaged section, welding in a new piece. This takes months of work. Meanwhile, the ship's structure is weakened. If another stress hits during repairs, secondary failures cascade. The entire structure might buckle, hull breaches vent atmosphere, crew sections decompress. Everyone dies in minutes. External repairs require spacewalks. Radiation outside the ship is extreme. Spacesuits provide limited protection. Astronauts on ISS limit EVA duration to 8 hours. Generation ship crew members might need days or weeks of continuous exterior work for major repairs. Radiation doses accumulate rapidly. Cancer risks skyrocket. The crew member volunteering for the repair might be signing their own death warrant. Will people sacrifice themselves for the mission? Sometimes, yes. Sometimes, no. When critical repairs depend on volunteers accepting fatal doses, the crew must choose between individual lives and collective survival. Psychological factors complicate repairs. After decades of travel, maintenance discipline might slip. Routine inspections get skipped. Small problems go unreported. Nobody wants to admit they made a mistake or overlooked something. By the time issues surface, they have become major crises. The culture of diligence required for survival might erode across generations. Complacency kills as surely as equipment failure. Yet even assuming perfect maintenance and unlimited spare parts, one final barrier stands immovable. Building a generation ship requires resources equivalent to a large nation's annual budget. Launch costs alone reach hundreds of billions. Spacecraft construction, testing, provisioning, all add more. Total mission cost approaches $1 to $10 trillion depending on assumptions. That is $1,000 billion to $10,000 billion. Numbers so large they lose meaning. For comparison, the entire Apollo program cost roughly $150 billion in today's dollars. That sent 12 people to the lunar surface for a few days each. A generation ship is thousands of times more complex. Costs scale accordingly. Funding must come from governments, corporations, or wealthy individuals. Each source has problems. Governments operate on election cycles. Politicians think in terms of 2, 4, or 6-year terms. Proposing a project that delivers results in 400 years is political suicide. Voters will not support it. The benefits are too distant. Immediate problems, healthcare, infrastructure, defense, always take priority. Allocating trillions to a starship when roads are crumbling and hospitals are underfunded is politically impossible. Democracy is incompatible with multi-century projects. Authoritarian governments could mandate funding regardless of public opinion, but even dictators die. Regimes change. New leaders have different priorities. A project started under one ruler might be cancelled by the next. China's Three Gorges Dam took 17 years and cost tens of billions, much shorter and cheaper than a starship. Yet, it faced political opposition throughout. A 400-year mission would almost certainly be abandoned somewhere along the way. Corporations demand returns on investment. Shareholders expect profits within quarters or years. A starship generates no revenue for centuries. The business case is non-existent. Even if the destination star system contains valuable resources, bringing them back takes another 400 years. Total timeline is 800 years minimum. No corporation survives that long. The oldest existing companies are a few centuries old at most. Expecting corporate commitment across millennia is fantasy. Wealthy individuals might fund it as vanity projects, space enthusiasts with billions to spare. But even the richest people have limits. Total global billionaire wealth is roughly $10 trillion. Funding one Starship mission consumes a significant fraction. Most billionaires would refuse. Their money goes to yachts, mansions, and foundations bearing their names. A starship that leaves long before results arrive offers no personal glory. Dead philanthropists get no satisfaction from discoveries made centuries later. Crowdfunding might raise billions, but not trillions. The largest crowdfunding campaigns raise tens or hundreds of millions. Scaling to trillions requires billions of contributors. That is a substantial fraction of humanity. Coordinating global contributions is logistically impossible. Fraud and mismanagement would siphon funds. The project would collapse under its own bureaucratic weight long before launch. Advocates argue the mission serves all humanity. Knowledge benefits everyone. Survival of the species justifies any cost. These arguments fail when confronted with present suffering. Telling a starving child that their starvation is acceptable because we need to build starships is morally monstrous. Resources spent on interstellar travel are resources not spent on immediate human needs. The ethical calculation is brutal and clear. Opportunity costs are staggering. $1 trillion could house every homeless person on Earth. It could end malaria, provide clean water globally, educate billions. These interventions save lives now, measurably, visibly. Choosing a starship over present lives is choosing the hypothetical future over the tangible present. Most people reject this choice. Some argue interstellar colonization ensures long-term species survival. Earth might face existential risks: asteroid impacts, supervolcanoes, nuclear war, pandemics, climate collapse. Spreading to other stars provides insurance. If Earth dies, humanity survives elsewhere. The counter-argument is simple. Those existential risks are addressable with far less money than interstellar travel costs. Asteroid deflection technology costs billions, not trillions. Pandemic prevention and response infrastructure costs hundreds of billions. Climate mitigation costs trillions, but benefits are immediate and local. Every dollar spent addressing Earth-based existential risks provides better return on investment than interstellar colonization. Fix the planet we have before attempting to reach others. Proponents counter that we should do both: address Earth's problems and build starships. Sounds reasonable until you realize there is no "and" in constrained budgets. Money is finite. Political will is finite. Attention is finite. Choosing both means doing neither well. Half measures fail. Better to focus resources on solvable problems with near-term benefits. The philosophy question emerges: why are we doing this? For whom? The people who launch see no results. Their children see none, nor their grandchildren, nor 10 generations beyond. The mission's purpose is abstract and distant. Humans struggle to care about such remote outcomes. Evolution did not design us for multi-century planning. Our brains optimize for survival within one lifetime. Expecting sacrifice for benefits 20 generations distant contradicts human nature. Still, some dreamers persist. They propose alternative approaches that sidestep human limitations entirely. Project Orion began in 1958. Scientists at General Atomics asked a wild question: what if we threw nuclear bombs out the back of a spacecraft? Each bomb explodes. The blast pushes against a massive steel plate attached to the ship. Giant shock absorbers cushion the crew. Repeat every few seconds. The spacecraft accelerates, using nuclear explosions as propulsion. The idea sounds insane. It also works. The physics is straightforward. Nuclear explosions release tremendous energy, convert even a small fraction into directed thrust, and you achieve impressive speeds. Calculations showed an Orion spacecraft could reach Mars in weeks, the outer planets in months, nearby stars within a century. No other propulsion concept offered comparable performance with 1960s technology. The design envisioned a massive pusher plate, perhaps 50 meters across, made of thick steel or tungsten. Shock absorbers, essentially enormous springs and pistons, connected the plate to the crew module. Nuclear charges, small bombs weighing perhaps 100 kilograms each, were ejected from the rear. Precise timing detonated them at optimal distance from the plate. The expanding plasma hit the plate, transferring momentum. The ship lurched forward. Shock absorbers smoothed the acceleration into something approaching continuous thrust. Early Orion designs used atomic fission bombs. Later proposals considered fusion bombs for higher performance. A Starship version might carry tens of thousands of nuclear charges. Each explosion provides incremental velocity increase. Together, they accelerate the ship to a few percent of light speed. Journey time to Alpha Centauri drops to 150 years or so. Still multi-generational, but much faster than alternatives. The engineering challenges are immense. The pusher plate must withstand thousands of nuclear detonations without breaking. Each explosion subjects it to extreme heat and pressure. Erosion occurs. The plate gradually vaporizes. Make it thick enough to last the entire mission, and it masses hundreds or thousands of tons. That mass needs acceleration, requiring more bombs, increasing total ship mass. The cycle compounds, shock absorbers must be perfect. Too stiff and acceleration spikes crush the crew. Too soft and the ship oscillates wildly. Finding the right balance is difficult. Components must work reliably for decades. Failure means the crew experiences sudden high G acceleration. Bones break, organs rupture. Everyone dies. Radiation is the killer problem. Nuclear explosions produce intense neutron and gamma radiation. The pusher plate absorbs some. Much passes through and bathes the ship. Shielding helps but adds mass. Even with heavy shielding, crew members receive significant radiation doses over years of pulse detonations. Cancer rates would be elevated, life expectancy drops, genetic damage accumulates across generations. Political and environmental concerns killed Project Orion. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear explosions in space. Launching a spacecraft powered by nuclear bombs became illegal. Environmental activists opposed the idea. The first launch from Earth would produce radioactive fallout. Tens of thousands of bombs detonating in Earth's atmosphere for several minutes during ascent would contaminate huge areas. Deaths from radiation exposure could number in the thousands. Assembly in space avoids atmospheric contamination. Launch components on conventional rockets. Assemble the Orion ship in orbit. Load the nuclear charges. Depart from orbit rather than Earth's surface. No fallout reaches the ground. The treaty still prohibits it, but treaties can be renegotiated if circumstances change. Fuel is relatively easy to obtain. Nuclear weapons exist in thousands. Disarmament treaties require destroying warheads. Convert them into Orion propulsion charges instead. Two birds with one stone, reduce nuclear stockpiles while enabling interstellar travel. Politically challenging but conceptually neat. The psychological aspect is terrifying. Riding a ship propelled by continuous nuclear explosions requires nerves of steel. Each detonation is a small earthquake. The ship shudders violently. Noise and vibration are constant. Sleep becomes difficult. Stress accumulates. The crew lives on a nuclear bomb disposal platform. One malfunction, one charge detonating at the wrong time or place, and the ship disintegrates. Everyone vaporizes instantly. Modern variations propose using fusion pellets instead of fission bombs. Inertial confinement fusion compresses tiny pellets of deuterium-tritium fuel using lasers or magnetic fields. The pellet implodes and fuses, releasing energy. Much cleaner than fission, less radiation. Smaller pulses allow smoother acceleration. The technology remains experimental. Achieving reliable fusion ignition is difficult. Scaling to thousands of successful ignitions is harder. The approach might work eventually, not yet. Project Orion proved interstellar travel is possible with mid-20th century technology. That realization is both hopeful and damning. We could build a starship. We choose not to. The barriers are political, economic, and social. The physics works, humanity lacks the will. Yet some suggest removing humans entirely solves most problems. Humans are fragile. We need oxygen, water, food, warmth, gravity, protection from radiation. We get bored, depressed, sick. We fight among ourselves. We die after a few decades. Sending humans to other stars requires solving hundreds of problems simultaneously. Every problem compounds the mission's complexity and cost. Robots need none of these things. No oxygen, no food, no water. Radiation does not harm them directly. It damages electronics, but shielding requirements are minimal compared to protecting living tissue. Robots do not get bored or depressed. They do not fight. They follow programming. Most importantly, they can be shut down during travel and reactivated upon arrival. No aging, no resource consumption. A robot sleeping for 400 years arrives as fresh as when it departed. The mass savings are extraordinary. A single human requires tons of life support, equipment, food, water, waste recycling, habitat space. Multiply by 500 people and the generation ship masses hundreds of thousands of tons. A robot probe masses a few hundred kilograms, 1,000 times lighter. Propulsion requirements drop proportionally. Fuel needs shrink. Launch costs plummet. Mission feasibility improves dramatically. Communication delays affect robots less severely. Humans need psychological connection. Robots do not. A robot can operate autonomously for years without contact from Earth. If something breaks, the robot either fixes it or fails. No panic, no fear, just systematic troubleshooting. If the robot cannot fix the problem, it dies silently. No suffering. Redundancy becomes cheaper with robots. Launch 10 probes instead of 1. If 9 fail, the 10th might succeed. Launching 10 crewed generation ships is impossible. Launching 10 robot probes is expensive but conceivable. Probability of success increases with numbers. The scientific mission remains viable. Robots can explore, collect data, transmit findings. They can sample atmospheres, analyze rocks, search for biosignatures. Many scientific objectives do not require humans present. Remote sensing and automated analysis suffice. Humans add value for complex decision-making and adaptation to unexpected situations. But modern AI is improving rapidly. Future robots might handle unexpected scenarios nearly as well as humans. The philosophical objection arises immediately. Sending robots is not colonization. It is exploration. Humanity does not spread. We do not become an interstellar species. We remain confined to Earth and maybe the inner solar system. Our future is limited by our star's lifespan. Eventually, billions of years hence, expansion beyond becomes necessary. Robots cannot save humanity. Only humans can. Counterargument. Robots can lay groundwork for later human missions. Send robots first. They arrive at the destination star system, survey planets, identify resources, maybe begin construction of infrastructure. When conditions are prepared, humans follow. This approach reduces risks for human travelers. They arrive at a star system already partially developed rather than completely unknown. Timeline is the problem. Robots traveling at 10% light speed take 40 years to reach Alpha Centauri. Another 4 years for signals to return. Total, 44 years. Then begins infrastructure construction. How long does building a habitat, life support systems, and landing facilities take? Decades, maybe centuries. Humans launch perhaps a century after the robots. They arrive a century later. Total timeline, 2 to 3 centuries from initial robot launch to human arrival. Nobody alive at mission start sees humans reach the destination. Political and economic support degrades across such spans. Alternatively, robots could carry genetic material, frozen embryos, or synthesized DNA. Upon arrival, robots construct artificial wombs, gestate embryos, and raise children using pre-programmed education. Sounds like science fiction. It is. Every step involves technology we do not have. Artificial wombs work for a few weeks in labs. Full gestation from embryo to birth is unproven. Raising children without human parents risks severe psychological damage. Who teaches language, social skills, and culture? Robots following scripts? The resulting humans might be deeply dysfunctional. Ethical questions arise. Creating children without parents in a robotic facility on an alien world seems cruel. These children did not consent. They are born into isolation, raised by machines, with no connection to Earth or human culture. Their lives serve a mission they had no say in. This arrangement resembles creating people as tools, morally repugnant. The alternative is bioengineering. Modify humans genetically to tolerate space conditions better. Radiation resistance, lower metabolic needs, enhance DNA repair mechanisms. Designer humans built for interstellar travel. The ethical concerns multiply. Who has the right to create modified humans? What are their rights? Are they still human or something else? Every solution creates new problems. Robots solve engineering challenges, but not the question of human expansion. Genetic engineering and artificial gestation attempt to have both but violate ethical norms. The dilemma remains unresolved. We can send robots easily. We cannot send humans practically. The gap might be unbridgeable with foreseeable technology. Some scientists cling to one last hope. Freezing someone preserves their body indefinitely. Cryonics companies offer this service today. Pay tens of thousands of dollars, and upon legal death, your body or head gets frozen in liquid nitrogen. The promise is revival decades or centuries later when medical technology can cure whatever killed you. In practice, nobody knows if revival is possible. The technology does not exist. It might never exist. Customers are gambling on future breakthroughs that may never come. Freezing damages cells. Water inside cells crystallizes. Ice crystals have sharp edges. They puncture cell membranes, shred organelles, destroy structures. Thawing does not reverse this damage. The cells are already destroyed. Vitrification offers improvement. Flood the body with cryoprotectant chemicals before freezing. The fluids vitrify, meaning they solidify without forming crystals. Damage reduces but does not eliminate. Toxicity from cryoprotectants poses problems. The chemicals are poisonous. High concentrations cause organ damage. Small organisms revive from cryogenic freezing sometimes. Wood frogs freeze solid each winter. Their hearts stop. Blood stops flowing. Ice fills their bodies. Spring arrives. They thaw, and they hop away. Special proteins in their blood prevent ice crystal formation. Cells survive intact. Humans lack these proteins. Engineering them into human genomes might work but introduces unknown risks. Modifying every cell in an adult body is far beyond current capabilities. Embryos freeze and thaw successfully. In vitro fertilization uses this routinely. Embryos at very early stages, just a few cells, tolerate freezing well. The smaller the organism, the better it survives cryopreservation. Single cells like sperm and eggs freeze well. Whole organs do not. Kidneys, hearts, and livers suffer severe damage from freezing. Transplanting them after thaw usually fails. Scale matters. Freezing a 70-kilogram human faces immense challenges. Some researchers propose suspended animation instead. Cool the body without freezing. Metabolic rate drops. At 10 degrees Celsius, metabolism slows roughly 50%. At 0 degrees, just above freezing, metabolism drops further. The person is alive but barely. Heart rate slows to a few beats per minute. Breathing almost stops. They age extremely slowly. Decades pass subjectively like years. Medical applications show promise. Trauma patients suffering severe injuries sometimes get cooled to buy time for surgery. Body temperature drops to around 28 degrees Celsius. This provides a few extra hours. Longer durations remain experimental. Keeping someone suspended for months or years involves risks. Infections develop. Blood clots form. Muscles atrophy even at reduced metabolism. Waking up after years of suspension might reveal a body too damaged to recover. Assuming suspended animation works, applying it to interstellar travel helps significantly. Crew members sleep during transit. No food or water needed. Life support requirements drop to minimal levels. Psychological issues vanish because they are unconscious. Only a skeleton crew stays awake, rotating shifts, monitoring systems. Even they sleep most of the time. A journey taking centuries passes quickly for sleepers. They age only a few years subjectively. Reliability is the crushing problem. Suspended animation systems must work flawlessly for centuries. One malfunction and sleepers die. The awake crew cannot fix complex medical failures. They lack expertise. If cryogenic equipment fails catastrophically, everyone in suspension dies simultaneously. The mission ends. All eggs in one basket, frozen together. Reviving from suspension after decades is another unknown. Thawing a human frozen for years has never been attempted. Animal experiments show mixed results. Muscle degradation, organ damage, neurological impairments all occur even with careful protocols. Reviving someone after a 400-year suspension might produce a brain-damaged, physically wrecked individual unable to function. They survive the journey only to become a living corpse upon arrival. Radiation affects suspended bodies just as much as active ones. Cosmic rays penetrate tissue, whether metabolically active or dormant. Damage accumulates. DNA strand breaks, pile up. Repair mechanisms are offline during suspension. Cells cannot fix radiation damage. After 4 centuries of exposure, chromosomes are shattered. Cancer becomes inevitable upon revival. The person dies within months from metastatic tumors. Suspended crew members are helpless. If the ship encounters problems requiring immediate action, waking them takes time. Hours, maybe days. By then, the crisis has resolved or killed everyone. Active crew must handle all emergencies alone. The suspended majority contributes nothing until arrival. It is not a crew. It is cargo, human cargo that must be maintained carefully lest it spoil. The ethical dimension returns. Putting someone in suspended animation for centuries without guarantee of revival is effectively killing them. They consent before departure, but consent is meaningless without full understanding of risks. Nobody understands the risks because nobody has done this before. The first human to attempt multi-century suspended animation is a guinea pig. If revival fails, they are murdered by the mission planners who assured them it was safe. Every proposed solution for interstellar human travel involves untested, dangerous technologies with significant failure risks. Accepting these risks requires desperation or bravery bordering on insanity. Most people choose neither. They stay home, they accept the limits, and the limits are stark. Alpha Centauri, the nearest star system, contains 3 stars. Alpha Centauri, A and B orbit each other. Proxima Centauri, a dim red dwarf, orbits the pair at a distance. Proxima hosts at least one planet, Proxima Centauri b, discovered in 2016. The planet orbits within the habitable zone where liquid water could exist. Mass is similar to Earth. It might be rocky. Initial excitement suggested this could be our nearest habitable world. Reality is less optimistic. Proxima Centauri is a red dwarf. It flares violently, emitting bursts of radiation thousands of times stronger than our star's flares. These flares bombard nearby planets with lethal doses of X-rays and ultraviolet light. Proxima b receives this constantly. Any atmosphere would be stripped away by the stellar wind and radiation. The surface is likely sterilized. Life as we know it cannot survive there. Tidal locking is another problem. Proxima b likely shows the same face to its star constantly, just as our moon shows one face to Earth. One side experiences eternal daylight, becoming scorching hot. The other side freezes in eternal darkness. Temperature extremes are enormous. A narrow twilight zone between might be temperate, but weather patterns would be bizarre. Winds carrying heat from the day side to the night side would blow at hurricane speeds constantly. Habitable does not mean pleasant. Even if Proxima b were genuinely habitable, the journey takes decades. At 20% light speed, breakthrough Starshot probes need 21 years. Slower, crewed missions take centuries. And for what? To arrive at a world probably bathed in deadly radiation, tidally locked, and atmosphereless. The destination might be worthless, but you cannot know until you get there. The mission is a blind leap, billions of dollars and years of effort potentially wasted. Beyond Alpha Centauri, other stars stretch into the void. The nearest few dozen stars sit within 10 to 20 light-years. Most are red dwarfs. Habitable planets around red dwarfs face the same problems as Proxima b, flares and tidal locking. A few are yellow stars like ours, but they are farther. Tau Ceti, 12 light-years away, has planets, but their habitability is uncertain. Journey times double compared to Alpha Centauri. Risks and costs multiply. The nearest definitely habitable world might be hundreds of light-years away. We do not know because observing exoplanet surfaces is nearly impossible with current telescopes. We detect planets by watching them transit their stars or by measuring gravitational wobbles. These methods tell us size and orbit. Atmospheric composition is detectable for some planets, but confirming water oceans, continents, and biospheres requires close-up imaging. That requires getting there. A mission to a star 100 light-years away at 10% light speed takes 1,000 years. 40 generations pass aboard the ship. The people who arrive are culturally disconnected from Earth. They might not consider themselves human in the traditional sense. Earth is ancient history, a mythical origin. Why should they care about reporting back to a civilization that existed a millennium ago? The void between stars is not empty, but functionally so. Average density is 1 hydrogen atom per cubic centimeter. Occasionally, molecular clouds increase density to hundreds or thousands of atoms per cubic centimeter. Still, almost nothing. Traveling through this near-perfect vacuum for decades or centuries, you see nothing. No stars visibly move. The destination star brightens slowly over years. Behind you, our star fades gradually. Otherwise, nothing changes. You are frozen in time and space. Progress is measured in decades per percentage point of distance covered. The psychological impact of such emptiness is incomprehensible. Navigation depends on distant quasars and pulsars. These cosmic beacons provide reference points. Calculating position requires observing multiple sources and triangulating. Errors accumulate over light years. By journey's end, your position might be uncertain by billions of miles. Missing the target star system entirely becomes possible. The ship overshoots and continues into deeper space, never finding another star within fuel range. Everyone dies slowly as supplies deplete. Bodies float frozen in the ship, a derelict tomb drifting forever. The emotional cost of interstellar emptiness is a barrier no technology overcomes. You cannot engineer away loneliness. You cannot design a system that makes eternal isolation bearable. Humans need connection, variety, novelty, purpose. The void offers none. It is cold, dark, silent, unchanging. The human mind was not built for this. We evolved on a vibrant planet full of life, sound, and movement. Asking people to endure the opposite for lifetimes is asking them to sacrifice their humanity. Yet distance itself reveals something even more profound about this endeavor. When Voyager crossed the heliopause, headlines declared it left the solar system. Technically incorrect. Gravitationally, it remains bound to our star. The Oort cloud extends light years outward. Voyager sits far closer. By the gravitational definition, Voyager is still home. It will be for tens of thousands of years. Different definitions create different boundaries. The heliopause marks where stellar wind stops. The Oort cloud defines gravitational dominance. Hill-sphere radius calculates where our star's gravity overcomes neighboring stars' pull. Escape velocity measures when an object travels fast enough to never return. Each definition gives a different answer for where the solar system ends. There is no single clean boundary. It is fuzzy, contextual, and arbitrary. Psychologically, Voyager left when it stopped seeing planets. When Earth became a pale blue dot, when familiar sights vanished and only stars remained. That happened decades ago. The spacecraft is beyond everything recognizable. To the human mind, it has left. Physics says otherwise. The dissonance is unsettling. Interstellar missions face the same ambiguity. Suppose a generation ship reaches Alpha Centauri and enters orbit. Did it leave the solar system? Physically, yes. Gravitationally, it is now bound to a different star. But culturally, the people aboard speak Earth languages, eat Earth-derived food crops, follow Earth-descended customs. They are humans from Earth living around another star. Have they left humanity behind? Or is humanity now an interstellar species because members live in two star systems? The ship itself is a piece of Earth, built from Earth materials, launched by Earth labor, designed by Earth minds. It carries Earth microbiomes in the bodies of crew members, bacteria in their guts, mites on their skin, spores in the air. The ship is a fragment of Earth's biosphere transplanted into space. In a sense, Earth has expanded. The solar system now includes a satellite 4 light-years away. Definitions of home blur across generations. First-generation crew members consider Earth home. They remember it, miss it, dream of it. Their children, born aboard the ship, have never seen Earth. Home is the ship. Earth is a story, a place in videos, not a tangible location. By the 3rd generation, Earth is mythology. Home means the ship and eventually the destination planet. Psychological departure happens generationally, even if physical departure happened instantly at launch. Language evolves. The crew speaks English or Mandarin or Spanish at departure. 400 years later, their descendants speak a dialect incomprehensible to Earth natives. Words drift, grammar shifts. New terms emerge for ship-specific concepts. Earth languages lack words for experiences unique to generation ships. The linguistic divergence parallels biological and cultural divergence. They are no longer Earth humans. They are ship humans. Upon arrival at the destination, do they belong to Earth or to the New World? They have never set foot on the planet. It is as alien to them as it is to Earth. They hover in orbit, strangers everywhere. The planet below is hostile. Earth behind them is unreachable. Home exists only aboard the ship. They are permanent exiles, belonging nowhere. The tragedy is profound. Colonization is supposed to expand home, not erase it. Terrestrial colonization kept connections to motherlands. Ships returned. Trade happened. Communication was slow but functional. Interstellar colonization severs all ties permanently. 4-year communication delays make conversation impossible. The colony is independent from day one. It cannot be otherwise. Help from Earth arrives too late if it arrives at all. Are interstellar colonies part of humanity? Do we share identity across light years and centuries? Philosophically, this is unanswerable. Biologically, they are humans. Genetically, they are our descendants. Culturally, they will diverge beyond recognition. The question, have we left the solar system, becomes, are we still us? Both questions lack clear answers. Some argue the question itself is meaningless. Leaving is continuous, gradual, and definitional. Voyager is leaving. It will always be leaving. It will never finish leaving. The process has no endpoint. Interstellar travelers are always in between, never fully departed from one place, never fully arrived at another. Permanent transition is their state. Home is motion itself. This realization brings the final, brutal truth into focus. We are not going anywhere. The distances are too vast. The energy requirements are too high. The biological constraints are too severe. The economic costs are too extreme. The psychological barriers are insurmountable. The timescales exceed human planning horizons. The technology is centuries away, maybe impossible. Every solution creates worse problems. Every proposal requires miracles. Advocates point to historical examples. People said heavier-than-air flight was impossible. Then the Wright brothers flew. People said atomic energy was fantasy. Then we built reactors and bombs. People said rockets could not reach space. Then we reached orbit, the moon, and beyond. Therefore, interstellar travel will follow. Just a matter of time and effort. The comparison fails. Aviation, nuclear energy, and rocketry involved incremental improvements on existing principles. We understood aerodynamics, lift, thrust. We understood nuclear physics, chain reactions, and energy release. We understood orbital mechanics, gravity, and propulsion. Interstellar travel requires breakthroughs in physics we do not have. Maybe faster than light travel via wormholes or warp drives. Maybe physics behaves differently than we think. These are not incremental improvements. These are fundamental revisions to our understanding of reality. Physics has been tested exhaustively. Relativity is confirmed by countless experiments. Quantum mechanics is verified daily in particle accelerators and electronics. The Standard Model explains almost everything we observe. Room for revolutionary breakthroughs is shrinking. We are not missing huge chunks of physics. We are refining edges. The likelihood of discovering a magical shortcut to the stars diminishes with every successful experiment confirming existing theories. Maybe we accept limits. Maybe interstellar travel is genuinely impossible for biological beings. Maybe the universe is structured such that intelligence remains locked to its birth star. Billions of stars hosting billions of planets, each potentially developing life and intelligence, all isolated permanently by distances too vast to cross. The galaxy is not empty. It is crowded with trapped civilizations, unable to meet, unable to communicate effectively, alone despite the company. This solves the Fermi paradox elegantly. If everyone faces the same barriers, nobody explores, nobody colonizes, nobody builds galaxy-spanning empires. Civilizations arise, flourish, and die on their home worlds. We see no evidence of aliens because none can travel here. We cannot travel there. The silence of space is not absence of life. It is the silence of imprisonment. The emotional weight of this conclusion is crushing. Humanity dreams of the stars. We tell stories of starships, colonies, adventures in distant worlds. Science fiction imagines futures where we spread across galaxies. It is inspiring, hopeful, and probably wrong. The dream sustains us. The reality is we are bound to Earth and, at best, to the inner solar system. Mars might host colonies. Asteroids might provide resources. The moons of Jupiter and Saturn could see outposts. Beyond that, probably nothing within the lifetime of our species. Our star will die eventually. 5 billion years hence, it will swell into a red giant. Earth will be incinerated. If humanity still exists then, it must leave or die. But 5 billion years is incomprehensibly distant. Species do not last that long. Mammals have existed for 200 million years. Modern humans for 300,000 years. Civilizations last centuries or millennia. Expecting humanity to persist billions of years is absurd. We will be gone long before our star dies. Something else, evolved from our descendants or created by us, might face that deadline. They are not us. Their problem, not ours. Perhaps artificial intelligence solves it. Machines designed to explore and survive without biological limitations. They journey to other stars, establish infrastructure, and await instructions or evolution into independent intelligences. Humanity ends, machines continue. Our legacy spreads, even if we do not. Is this success? Depends on how you define success. The genes and ideas are ours. The entities are not. We created our successors and exited the story. The honest assessment is grim. Interstellar travel for humans is almost certainly impossible with any foreseeable technology. Robot probes might reach nearby stars. Returning data to Earth might happen within lifetimes. But humans standing on exoplanets? Generation ships arriving at distant suns? Probably never. The universe is too large. Physics is too constraining. Biology is too fragile. Economics is too demanding. We are stuck here. We always were. The dream was beautiful. The reality is isolation. Facing this truth requires courage. It means abandoning comforting fantasies and accepting limits. It means investing resources in problems we can solve instead of chasing dreams we cannot. It means making peace with being a single planet species, temporarily spreading to nearby moons and planets before inevitable extinction. It means the universe is incomprehensibly vast, and we will see only the tiniest fraction of it. Maybe that is enough. Maybe exploring our solar system, understanding our cosmic neighborhood, and creating meaningful lives here should satisfy us. The alternative is spending trillions chasing impossible goals and failing. Accept the boundaries, work within them, find meaning in what is achievable rather than lamenting what is not. The stars remain beautiful. We can observe them, study them, understand them from a distance. We do not need to visit to appreciate their existence. Looking up at the night sky, knowing each point of light is a distant sun, perhaps hosting worlds, perhaps hosting life we will never meet, creates a sense of wonder that transcends physical exploration. We are connected to the cosmos through knowledge, even if not through travel. Will we ever leave our solar system? A few probes might. Humans? No. The answer has always been no. We just did not want to believe it.